Let's start with the simple problem. Okay. So we have a 15-meter beam with 200 kilonewton load on it. Looks pretty symmetric. Anybody spot what the reactions will be? Yeah, 100 on each side, right? Okay. How many regions do we have different equations in? How many loading regions would we say we have in this beam? 3. 1, 2, 3. Okay. So I'm going to go ahead and put my shear diagram right underneath it. Bending moment diagram underneath that one. Okay. Now let's do the free body diagram for region 1. Everybody good with this? Okay, so we just write our force summation equation. Some of the forces in the y have to be 0, so we'll have 100 minus v equals 0. What's v going to be? 100. Okay. Let's sum the moments. And remember our cut here is x away. So we'll sum the moments about the cut always. Counterclockwise is positive. We'll have the moment at the cut, m, minus 100x equals 0, or m equals 100x. Right? Everybody see where I'm getting these? Okay. So then let's plot those in region 1. So in region 1, at 0, I have 100 kilonewtons. And that doesn't change all the way across. Okay. In region 1 of the moment diagram, I have m is equal to 100x. So at 0, it's 0. At 1, it's at 100. At 5, it'll be at 500. Right? Everybody okay with this? Okay. I'd like you to do region 2. Okay, so let's pause and you do the free body diagram and equations for region 2. All right, anybody get some equations they want to share? Some of the forces in the y equals 0. What'd you get? Excuse me? Max, I heard you. 100 kilonewtons up minus 100 kilonewtons down minus v equals 0. So v equals 0. And let's sum the moments about the cut. Set that equal to 0. Anybody get this equation? We'll have the bending moment m
minus 100x.
minus 100x
plus 100 times x minus 5.
plus 100 times x minus 5 equals 0. Very good, right? And the x minus 5 comes from the fact that this is 5, so that makes this distance x minus 5, right? Okay. So if you solve this, Michael, what'd you get for m equals?
I got negative 500. Because 100x cancels with minus 100x.
Yeah, minus 100x plus 100x minus 500, but then we take it to the other side, so it'd be positive 500 kilonewton meters, right? Okay. So now let's plot these in region 2. So for region 2, it looks like v is 0. And m is 500, which is what we were at. It just goes flat. Okay. So then the last region we need to do sum of the forces in the y equals 0. We'll have 100 minus 100 minus 100 minus v equals 0, or v equals negative 100 kilonewtons. And then we can sum the moments about the cut, and that equals 0. So we'll have the moment about the cut plus 100 times x minus 10 plus 100 x minus 5 minus 100x, right? Equals 0. So this is for the closer one, this is for the further away one, and this is for the reaction at the end. So let's see, we'll have 200x minus 100x, so m is going to equal negative 100x. This would be minus 1,000 minus 500, so plus 1,500. Okay. So now let's plot these. At x equals 10, we'd have 500 for the moment, right? 1,500 minus 1,000. And then we're going down like so. Okay. And typically we connect our graphs at their discontinuities and then shade between the x-axis and the graph. Okay. All right. I want you to spend a minute and look at the loading diagram, the shear diagram, and the moment diagram and see if you can relate any of their values to each other. What happens in the shear diagram when I hit 100 kilonewton up load at 0? It jumps up to 100, right? And then it stays that way until it hits another load, and then what happens? It jumps in the direction of that load, right? Stays the same till I hit another load, jumps in the direction of the load, stays the same, jumps back up. Okay? So when you have a point load or a reaction in your loading diagram, that causes the shear diagram to jump in the same direction. Okay? So my shear diagram is going to jump up 100, stays the same, jumps down. Okay? Now how about the moment diagram? What's the value of the shear diagram right here? 100. Okay? What's the value of this right here? 500. How far have we gone? 5. So what's the slope of this line? 100. Okay? Is it positive or negative? Positive. Okay, so the slope of the moment diagram turns out to be the value of the shear diagram. So notice that the shear diagram has a value of 100. That says our slope then is 100 in this region. Here our shear diagram has a value of 0. Slope is 0. Here it has a value of negative 100. Slope is negative 100. Okay. How much did we change here? We went from 0 to 500. What's the area underneath the shear diagram? 500. So the change as you go across the beam is the area underneath the shear diagram. Okay, so let's put those in calculus terms, right? So the slope of the moment diagram, dm dx, is just equal to the value of the shear. The change in the moment diagram is equal to the integral of the shear. Right? The integral gives us the area underneath the curve. Okay? All right with these? Okay? So this is one shortcut. Let me do another. Let's do another one to show you a second shortcut. When you have a distributed load. Okay. Can anyone just see what the reactions at A and B are going to be on this guy? I can't. So go ahead and solve for the reactions at A and B. Did you get some equations like this, hopefully? What'd you get for AY and BY? 236?
Yep.
AY is?
Yeah. AY is 236, BY is 163.
Okay. AY is 236 and BY is 163, and that'd be kips, right? Doesn't? Okay. Okay. All right, so how many loading regions do we have? 3 again, right? 1 here, one here, one there. Okay. So, let's see here. Let's go ahead and do the first one. Something like that, right? Okay. So now, sum the forces in the y. Looks like we'll have 236 minus 50 times x minus v equals 0. So v is equal to 50x minus, oh, nope, it's equal to negative 50x plus 236.
Hey, Andy.
Yeah.
Why do you put the distributed load instead of putting the resultant force and then finding the divisions that way?
Because, so the question is, why do I put the distributed load and instead of just finding the resultant force here? Because what we're doing is we're in region 1 here, so we're maybe cutting it right there. And so we have to account for the load that's on just the portion we're talking about. So we're cutting at some distance x that isn't the full 6 feet.
Okay.
Right? And so if I just put that single, if I consolidated this 50 kip per foot times 6 is 300 kip, and I put it right here in the middle of that, and then I looked right here, I'd say, well, there's no load on it. But that's not true because there's distributed load.
Gotcha.
Right? So we have to wait until we've actually sliced it to do that. Good question. Okay. So it looks like v is negative 50x plus 236. Let's go for some of the moments now. Some of the moments about the cut has to be equal 0. Counterclockwise, we'll have m minus 236 times x. Right? So that's this 236 here, plus 50 times x, that would give me the resultant of this, times its distance, which is x over 2. Right? So 50x is just giving me the resultant force here. Right? That'd be 50x. And its distance then, the lever arm from the cut face, would just be x over 2, because it's centered.
Can you explain the x over 2 a little bit more?
Sure. So in a rectangular distributed load, the resultant goes in the middle, right?
Right.
So the total length of the beam here is x. So for it to be in the middle, then it would be x divided by 2. It'd be 1/2 the total distance.
Okay, so for the moment we use the resultant.
So it's just the resultant of the
Of the x.
distributed load cut at some random place x,
Okay.
right?
Right.
Okay.
The 50x gives you the force, and max just gives you the distance from the cut.
Yep. So this is F times D. Okay. So we can say that the moment then is equal to 236x minus 25x squared. Okay. So I kind of did a boo-boo and put this here, but we're still going to put our shear and moment diagrams over on this side. Okay. Here's shear. Here's moment. Let's plot the shear diagram first. It says that we have negative 50x starting at, but the y-intercept is 236. So we'll come up to 236. And then we're going to go down at 50 and we're going to go across 6. So 50 times 6 is 300. So we're going to go from 236 to negative 64, I believe, as we go across 6. So we're going to end up about here, something like that. Okay? Our moment, we're going to start at 0, and it's going to be 236x minus 25x squared. So that's concave down, but at 1, it would be, what, 211. So it's going to be concave down, but going up. What's it going to be at 6? I can't do that in my head. What's 236 times 6 minus 25 times 36? 516? And what is well, so we're going to call this 516, right? What is it at 4 or at 5? $555, so it's more, right? So this thing does something, I don't know what it even looks like that maybe? I don't know. Okay. Let's do the next region. Okay. So some of the forces in the y will have 236 minus 300 minus v equals 0, or v is equal to negative 64, right? And then we can sum the moments about the cut. We'll have the reactive moment plus 300 times x minus 3. You can tell me where x minus 3 comes from. So it's the middle of this. This is 3, right? So then this is x minus 3. I could not see those when I took this class. It was so hard for me to get those. Okay. What else do I have? Minus 236 times x equals 0. So in this section, the moment will be equal to 300x minus 236x. That'd be negative 64x by the time it went to the other side, plus 900, right? Okay, so now let's plot that. It says the shear stays at negative 64, so we just draw a straight line. The slope of the moment is at negative 64x, and we are at 6. So what's negative 64 times 6 plus 900?
516.
516, that's where we were. So we just have this downward slope, and we're going to go 3 feet, so we're going to go down 192. What's 516 minus 192?
324.
Okay, 324. All right. Then we can do our last piece. Add everything up in the y. I'll have two. Nope, because so when we're cutting these, right, we're saying we're cutting it someplace in this region, and by is the boundary of the next region. Same thing with this 100 kip. Why we neglected that is we're in between the two. Okay. So some of the forces in Fy, we'll have 236 minus 300 minus 100 minus V equals 0. So it looks like V is negative 164. And let's sum the moments about the cut. So summing the moments about the cut, I'll have the moment at the cut plus 100 times x minus 9 plus 300 times x minus 3 minus 236 times x equals 0. So this tells us that the moment is going to be equal to negative 164x 900, oops, yeah, negative 900 is negative 1800 plus 1800. Okay. And if we plot these, what we're going to see this should have been a little shallower, and this is a little steeper, something like that. Okay? And here is my plot. Okay? So let's evaluate our two things that relate these graphs that we learned above, and that was that the slope of the moment diagram is the value of the shear. That's the first one, okay? So the shear here is going from a positive 236 down to 0 and then negative. And so our curve is very positive, decreasingly positive, goes to 0 right here, the point of inflection, and then decreases a little bit more, right? Then it has a constant downward slope in this region, and then more downward slope in this region, because the slope of the the slope of the moment diagram is equal to the value of the shear. Then we also said that the change in the moment diagram is equal to the integral of the shear diagram. So that means that the area underneath here gives me the change to here, right? The area underneath here gives me the change as I go from here to there. Okay? Now, there are two similar equations for how we relate the loading diagram to the shear diagram. And that's this. The slope of the shear diagram, dV dx, is equal to the magnitude of the load intensity, which we call Wx. So where we have a distributed load, note that this is 50 kip down. So its intensity is 50. The slope of this curve is negative 50. Okay? So if I know, if I have a distributed load that's constant, I know that that gives the shear diagram a slope of that intensity in the negative direction. So it's negative 50 down. Similarly, the change in shear is the integral of the loading diagram. So here I have an intensity of 50. The integral is just the area underneath the curve, right? So 50 times 6 is 300 as I go from 0 to 6 feet. If we look at my shear diagram, I go from 236 to negative 64, a change of 300 downward. Okay? Then I jump at the 100 kip, I jump down 100, and we're in business. Okay? This is called the graphical method for doing shear and moment diagrams. Let's try several doing this because it is way faster usually. The only time I use equations is if I need to know exactly where this point is, okay, the point of inflection on the curve where the maximum moment is, or if my distributed load is a triangle. Okay, because if it were a triangle, this becomes a cubic. Okay, so let's try a couple graphical ones that we can do. Okay, so three forces, 25, 50, 25. So we can by inspection see that my reactions will be what? Yep, 50 aside. Okay. Shear. Do this by looking at my loading diagram. I jump up 50 right at 0. Nothing happens. There's no distributed load until I get to 25 and I jump down 25. Nothing happens until I get to 50 and I jump down 50 to negative 25. Continue across, jump down another 25 to negative 50. Continue across, jump back up. That is much quicker than drawing 4 regions, right, and doing a shear moment diagram. Now, can we get the moment diagram from that? You bet. Okay. What do my equations tell me? What is the slope of the moment diagram? It's the value of the shear, right? So it's a positive 50. What's the change in the moment diagram as I go? Oh, I should probably put some measurements on here. Let's make each of these 3. So what's the change in the moment diagram as I go from 0 to 3? No. Change in the moment diagram is the area underneath the shear diagram. So what's the area underneath the shear diagram from 0 to 3? 150, right? And it's positive. It's above this axis. So I have a slope that's something like this. And I get to 150 because it's just 3 times 50. What happens now? Does my slope get steeper or shallower? Shallower, right? Because it decreases to 25. So I have half the slope. How much change do I have? Area underneath the curve, 3 times 75. So that means I go up to a max of 225. What happens from 6 to 9 meters? Positive or negative slope? Negative. Okay. Change of 75, I'm back to 150. And then lastly, back down. Okay. It's not so bad, right? Okay, let's do another one. Decided to build a really sweet tree fort. In my really sweet tree fort, I'm going to put a hot tub. Okay? Alright? Because it turns out, actually, you don't get like nice little graphs where it's just like, here's the load, here's the load, here's the load. Like, those actually represent something sitting on it, right? So this is my really sweet hot tub. Okay? And that's a distributed load, right? It's not a point load. Let's say the hot tub, it's a party hot tub. Make it 8 feet wide. Okay? And I'm going to center it in this beam. And I'll put 6 feet on each side. Right? So we can hang out in my tree fort hot tub. And yeah, it's going to be great. So I need to size this beam. I'm going to say that the hot tub has, oh gosh, per foot there, I'm going to say it's probably like 500 pounds a foot. Okay? Water's heavy. Okay? So it's 500 pounds a foot. So I believe 500 times 8 is going to be 4,000. So that means there's 2,000 pounds up here. That's 2 kip. And 2 kip. Okay? I'm going to say that we're going to be able to do this with just this information. What happens at the reaction of 2 kip in our shear diagram? We jump up 2 kip. Okay. Does anything happen in the next 6 meters or 6 feet? Nothing happens, so we just stay there. Okay. When we get to 6 feet, though, we have this distributed load. Do we jump down? No. What's the distributed load tell us? It's a slope. So we have a slope of negative 500. okay? And we're going to do that slope for 8 feet. So 8 times 500, that's the change we'll experience, is 4,000. So I'm going to end up at negative 2 kip. Okay? Then nothing happens, and I jump up. Okay? What's my moment diagram going to look like? With straight sides or rounded sides?
Straight sides, gotta get close to the top.
Yeah, so it's going to be like a flying saucer, right? So it's going to be a slope of 2 kip per foot, a change of 2 times 6, that's 12 kip feet, as we go from here to this point right here. As we, in the first 6 feet, we're going to do something like this, where we'll get to 2 times 6, or 12 kip feet. Okay? Then I need to figure out what's happening in here. Well, I have a positive but decreasingly positive slope. Is it tangent?
Yes.
Yeah, it is tangent. Okay? So we're going to have something that does this. Right? Comes down tangent on this side. Something about like that.
What do you mean by tangent?
I mean that the slope here in this region is continuous as I go around the curve. Because, see, the slope here is 2 kip. And if you looked at the just negative and just positive side of that, it's still 2 kip. Okay? So it's tangent. This line goes straight, and then it has a tangent curve that it just smooths. It's a continuous function as it goes around there. Okay? Now, what's the value of that peak? Because that's what we care about, right? We want to size the beam appropriately so that I don't go tumbling down out of my treehouse in my hot tub. I would be one weird duck if I did this. I'm not going to lie. Okay. 12 kip feet. How do I figure out what this point is? What's that, Max? Okay, so it's where V is 0. So I could figure out the change here. So I know that this is probably 4 feet in, right? So I could figure that it's 4 times 2 divided by 2. So it's 4. Right? 4 times 2. I'm just finding the area of a triangle where one side is 4, one side is 2. So it's 2 times 4 divided by 2, which is just 4, right? So I'm going to go up to 16 kip feet. That is my maximum bending moment. How else could I have done this? If with my graph I identify, hey, this is the point I want to know, how else could I do this? Yeah. So you could also, though, just cut your beam right there. Right? And draw the free body diagram again, where you have 2 kip, and you have half that distributed load. Right? And we know that this occurs, we decided, at 10 feet. So then we're just trying to find the bending moment, right? And I know this is 500. So I could just solve for the bending moment right here, and it would give me 16 kip feet. Okay. All right. Let's do a couple others. I'll have you work this one now. Okay? Find the maximum bending moment in this beam. So I'm going to tell you the fastest way to do that is to draw the shear and moment diagram, figure out where the maximum bending moment is based on your moment diagram. Okay, and you can use your graph to figure out what its value is. Excuse me? 5,000 pounds is the concentrated load, and 200 pounds per foot is the magnitude of the distributed load. The beam is 10 long. Okay, 2, 2, 4, 2 are those numbers. Okay? So I'm going to let you work on that for about, I don't know, 5-10 minutes. Anybody got reactions yet?
Yeah.
What'd you get at A?
4320.
4320 pounds.
1480.
1480. Okay. So from these, we can construct our shear diagram. So we jump up 4320. Nothing happens till we hit 5,000. We jump down 5,000. That'd take us to 680, I think.
Yep.
Nothing happens then till we hit this guy. Then we have a downward slope of 200 pounds per foot, a total change of 4 times 200 or 800. So we're going to slope down like this to 1480. My graph is not very to scale, but that's okay. And then, thanks Travis. Then we come across with nothing happening and jump up to 1480. Okay? That's not so bad. Everybody feel comfortable with their shear diagram? Okay? Moment diagram then. We're going to be linear in the first part? Yep. What's the change going to be? 4320 times 2, so 8640. Is that right?
Yep.
So I'll have a super steep slope up to 8640. Then I'll have a negative slope of 680 times 2. So 680 times 2, where do I go to right here? Someplace about here, right? What's the value there, Travis? 7280? Okay. Then we need to find how much I change, what happens from here to here. It becomes a curve, right? Because I start with a tangent slope that's increasingly negative. So it's going to do something like, and then like that, approximately. Beauty, eh? Beauty.
Looks good.
Okay. So what is my maximum bending moment? 8640.
Is that another tangent slope at the end?
Yeah. And that would be foot pounds. Okay. So yeah, you can tell that it's a tangent slope because it's a continuous graph here.
Sure, but why from the second to last segment to the end is it also tangent slope? Because that graph is.
Again, because it's continuous here. Because this goes to a negative,
Right, but then it levels off to the end.
right? So then it stays the same.
So on the moment, is that linear?
This piece here is linear. And it should be tangent to this.
Oh, gotcha. That's
Yep. Okay.
It's a hard picture.
So how would you go about finding the value, like on the third, for the point between section, at the end of the third section? So like that one.
Right here?
Yeah, like would you cut it up to a triangle and a rectangle and find the area underneath? And then add those and get.
Oh, to find the change?
Yeah, to get a value for your endpoint on the moment.
I'd actually start from the other end in that case because I have a box here. And so I would say that I go up the area of this box to there. But yes, you could also do that, find the area of the little one and find the area of the triangle, and that will give you the change negative in that direction. Yep. Okay. So our beams aren't always like this. Okay. Sometimes we have a beam comes out of a wall like this. And has 1,000 pounds here and 1,000 pounds here. And 3, 3, 3. Okay. So, what's the reaction at A going to be? Or how about the reaction at B? Now you can look at it and figure it out. Reaction at B has to be 2,000, right? Why does it have to be 2,000? Yep, because there can't be any y component here, right? Because these guys, if I sum the moments about B, they cause zero there's no moment, right? So that means the only location for my reaction is right there, okay? It'd be okay though if you didn't just see that and you solved it on the exam. Don't like freak out if you don't just see something. I might not give you something that you can see, right? So I'm just doing that because right now I'm not trying to teach you about summing the moments to find the reactions. I'm trying to teach you about shear and moment diagrams. Okay. Shear moment. So, what happens at the beginning? Nothing. Absolutely nothing. Then we come out, come to 1,000. At 3, we drop down 1,000. Come over to 2, jump up. Go over to the end and drop down. What's our bending moment look like then? Well, we've got nothing going on here until we get to right here. Then we have a very negative slope. So our bending moment's going to be a constant negative slope going down. The change underneath it's going to be 3,000. Boom.
Yeah.
So this is negative 3,000. Then what happens? Do I keep going down?
Nope. Goes up in the other
No.
direction.
Goes up in the other direction. Okay. One more thing we got to cover. Mm-hmm. What about when we have a couple moment applied? Okay. Yeah, so it does stuff, right? It changes things, okay? So what would the reactions in this guy be at A and B? They're each 2,500. Okay. Now, if I draw the shear diagram, I jump up 2,500. Nothing changes in shear till I get to 5,000. I drop down, go across, get to 2,500. Okay? So those couple moments don't do anything, which makes sense because remember, a couple moment is just saying that in this case I've got a force going down and a force going up, so their net shear is 0, but their net twisty is 1,000 foot-pounds. Right? Remember that a couple moment is just the same as having two forces in equal and opposite directions. They cause a twist, but they don't cause any shear. Okay? They cancel each other out in the shear department. But when we come over here to the moment, they cause a jump in the moment. How that works is a clockwise moment causes a positive jump in the shear diagram. So here we are at 0. We've got a positive 2,500 slope, right? So we know we're going up. And between, I guess I got to put some measurements on here. Let's make the whole thing 10 feet. Okay, so this happens at 2.5 feet, 2.5, and 5. Okay. So as I go from 0 to 2.5 feet, I'm going up like this. What's 2.5 times 2,500? 625, 6,250? Right? Okay. Then I hit a clockwise moment. That causes me to jump up the magnitude of that moment. So I jump straight up. Boom, just like a concentrated load. I jump straight up to 7,250. Then I keep going along my merry little way, which is like this. And the change is going to be another 6,250. So that'd be 12, 13, 14,000, I think, is what I end up at. Okay. And now I have a negative slope going back down. This is counterclockwise, so I jump down that much and keep going back down. And this little spaceship, rocket, is what my moment diagram would look like. Okay? So clockwise moments cause positive jumps in the moment diagram. Clockwise moments cause positive jumps in the moment diagram. Okay? It's a little counterintuitive since we always say counterclockwise is positive in a moment. This is clockwise. Couple moments cause a positive jump in the moment diagram. All right? So, you have a midterm on Monday. It will include shear and moment diagrams. I will not specify whether you need to do it by equations or by the graphical method. Okay? It may include something that's a whole lot easier to solve using equations. I don't know. I haven't written it yet. Okay? So I want you to be familiar with both the equation and the graphical method for doing shear and moment diagrams. It will include a frame machine problem. It will include a truss problem. How can you tell the difference between a truss problem and a frame machine problem? Two force members. Trusses only have loads applied where? At the joints. Okay. And we'll do static equilibrium and I might even say in 3D. Okay. Maybe 2D, we'll see. Okay. 2 or 3D static equilibrium problem. All right? That'll be the midterm. Okay? Have a good weekend.